All right, let's talk about AI assistants, because they're about to get a serious upgrade. I mean, we're way past just asking for the weather. Imagine an AI that can actually use your apps for you. Yep, let's get into it. Seriously, just stop and think about that for a second. What if your AI assistant could really do stuff? Not just, spit back a search result or set a timer, but actually take action. Exactly. We're not talking about small stuff here. Imagine you just say, hey, find and book me a flight to London for next Tuesday. And then you just watch as your phone does it. It opens the app, types in the details, clicks through all the pages, and bam, booking confirmed. Well, that's the kind of future we're diving into today. And it's all thanks to a brand new AI model called UI Venus 1.5. The whole idea behind it is to create less of a digital talker and a whole lot more of a digital doer. So you might be wondering, why don't we have this already? It seems like a no-brainer, right? Well, it really boils down to a pretty big roadblock in how our current assistants are built. Okay, so on the left, you've got what assistants can do now. They're kind of stuck in their own little world, right? They can answer questions, play music, but that's about it. But on the right, that's the dream. That's what we wish they could do. We want them to use our apps, handle complicated jobs, and most importantly, understand what's on the screen, just like we do. That ability to actually see and interact with the screen, that's been the huge missing piece. And that is where a totally new kind of AI comes into the picture. It's built specifically to solve this problem, and it's called a GUI agent. So what the heck is a GUI agent? Well, here's the key. It doesn't need some special, complicated access to an app's code. Nope. It literally just looks at your screen, just like you do. It sees the buttons, it sees the text boxes, and it figures out where to click, type, and scroll to get the job done. It has to actually find the submit button or the search bar visually. In the world of AI, they call this grounding. Basically, its understanding is grounded in what it can physically see on the screen. And all this info, by the way, comes directly from the technical report published by Ant Group's Venus team. This is the paper where they introduce UI Venus 1.5 and break down exactly how they built this incredibly powerful new agent. Okay, so how on earth do you train an AI to do something so human? Well, the secret sauce here is this really clever three-part training process they came up with. It's what gives this AI such a deep, intuitive feel for how apps actually work. First up, mid-training. The model basically went to school. It studied this enormous library of 10 billion pieces of data from over 30 different app data sets. You can think of it like an AI intern that was forced to read every user manual and watch every tutorial on the planet to learn the basics. Then came the real test, online reinforcement learning. This is where it learned by doing. But here's the cool part. It only got a reward, a good grade if you will, if it completed the entire task successfully, not just for one correct click. This forces it to think strategically about the whole mission, not just the next step. And finally, model merging. They took 3 specialized AIs, one that was an expert at grounding, one for web apps, and one for mobile apps, and they merged them all into one unified super agent. So it's this combination of massive book smarts, strategic, real-world practice, and then bringing together a team of experts that makes it so powerful. Okay, that training process sounds super impressive, for sure. But here's the million-dollar question. Does it actually work? Is it really any better than the other models out there? So naturally, the team put it to the test. They basically set up a digital Olympics, pitting UI Venus 1.5 against all the other top AI agents on a series of really tough challenges, or what they call benchmarks. And wow, the results speak for themselves. In all these charts, you're looking for the blue lines and bars. That's our champion, UI Venus 1.5. And as you can see, it doesn't matter if the task is navigating a super complex app or that grounding skill we mentioned, actually understanding the screen. It is consistently crushing it. It's right at the top or very, very close. Let's zoom in on a huge one. On this test called the Android World Benchmark, which is a brutal test across a ton of different real Android apps, it hit a 77.6% success rate. That's not just good, that is a new state-of-the-art performance, the best we've seen so far. But is it just getting lucky with its clicks, or does it get what it's looking at? That's what a grounding test is all about. And here, it scored a 75% accuracy in pinpointing specific things on the screen. That proves it's not just blindly tapping, it's genuinely comprehending the visual layout. And just to really drive the point home, on another really tough test called ScreenSpot Pro, it still nailed nearly 70% accuracy. So the big takeaway from all these numbers is pretty clear. This isn't a one-trick pony. Its performance is solid, it's repeatable, And it's versatile across all sorts of different digital hoops you make it jump through. Okay, so state of the art sounds fantastic in a lab. But what does all this power actually mean for you and me, like in our actual day-to-day lives? This is where things get really, really cool. The paper talks about it being able to handle all the stuff we do every day. Booking tickets on a travel app, buying something from an online store, even finding a specific recipe on a cooking site that matches exactly what you want. Basically, just think about any annoying multi-step thing you have to do in an app. The whole point of UI Venus 1.5 is that you can just give it one command and it'll take care of the rest. So this kind of technology is clearly starting to leave the research lab and head out into the real world. And that leaves us with a really fun question to chew on. Once you have an AI that can finally do things for you, what's the very first, most annoying, tedious task on your phone you're going to make it do?
Welcome to The Explainer. Today, we're diving into a new AI model that's trying to solve one of the biggest headaches in artificial intelligence, that painful choice between having incredible brain power and incredible speed.
So let's just jump right in with the big question, right? For the longest time, it's felt like a law of physics in AI. Why can't the smartest model also be the fastest? Why are we always forced to choose?
I mean, this has been the dilemma for years. You've got these frontier models. They are the supercars of AI. They can do these breathtaking feats of complex reasoning. But they are incredibly slow, outrageously expensive, and need entire server farms just to run. They're just not practical for the kind of fast, everyday tasks we need them to do.
But today, we're going to unpack a brand new model that might just break that trade-off. We're going to start with that power dilemma, then we'll meet our new contender, uncover its secret weapon, see how it actually stacks up against the big guys, and then, most importantly, talk about what this changes for all of us.
All right, let's meet the star of the show. This new AI is called Step 3.5 Flash, and it is making some serious waves. And you know, right out of the gate, its creators made a really bold claim. They said they built a model with agentic intelligence. That's a fancy way of saying an AI that can actually do stuff, not just talk, but without that crushing, bank-breaking computational cost.
So really, the promise is simple but huge, to give us the raw intelligence of a giant heavyweight model, but with the speed and agility of a world-class sprinter. It's trying to be the best of both worlds.
Okay, so how in the world does it pull off this magic trick? How can you have this enormous brain but run it like it's something small and nimble?
Well, the secret sauce is a really clever design called Mixture of Experts, or MOE. Now, instead of firing up the entire massive neural network for every single little thing, MOE acts like a super smart project manager, sending each task only to the small, specialized teams that are perfect for the job.
Here's a great way to think about it. Imagine a massive consulting firm with hundreds of specialists. You've got lawyers, engineers, marketing gurus, the whole shebang. If you have a legal question, you're not going to waste everyone's time by asking the entire company, right? No, you go straight to the legal department. Mo.io does exactly that, but for AI.
And here's how that process works, step by step. A task comes in. A little router inside the AI takes a look and says, okay, for this specific problem, I need you, and 6 other experts. It picks the best little team of 8 specialists for the job. Only that small group gets to work, while everyone else just chills, saving energy. It's incredibly efficient.
Now, this whole setup allows the model to have a massive total knowledge base. We're talking 196 billion parameters. That's where it gets its deep understanding and its powerful reasoning skills. It's a true giant.
And this is the flash part, for any one task, it only activates about 11 billion of those parameters. So you get the wisdom of the 196 billion parameter giant, but with the speed and cost of a much, much smaller model. It's a genius way to have your cake and eat it too. Okay, that all sounds fantastic in theory, but the real question is, does this clever design actually hold up in the real world? Let's see what happened when they put Step 3.5 Flash in the ring with the industry's reigning champions. And let me tell you, the researchers did not pull any punches. They put this model through a gauntlet of tests, benchmarking it against some of the biggest names you can think of to see if the theory really works in practice. This chart pretty much tells the story. Step 3.5 Flash is the one in the blue striped bars, and it's going head-to-head with behemoths like GPT 5.2 and Gemini 3.0 Pro across a whole bunch of really tough challenges.
And look at these results on reasoning. We're talking about incredibly difficult math and coding problems, the kind of stuff that is a true test of raw intelligence. And it's not just keeping up, it's right there at the absolute top of the pack, sometimes even beating models that are way bigger and more expensive.
And it isn't just a brain in a jar. When it comes to those agentic tasks, the stuff where an AI actually has to do things like write software or navigate a website, it proves, once again, it's not just smart, it's incredibly capable, posting scores that put it firmly in the top tier.
Now, anyone in the field will tell you building a mixture of experts model this big is notoriously hard. They can be really unstable and just fall apart during training. So how on earth did they manage to build this one so well?
Well, they did it with extreme, almost unheard of stability. Just look at this graph. This shows the training process over 17 trillion tokens of data. See how smooth that curve is? It's practically perfect. The paper even notes there was only one single tiny hiccup in the entire run. Honestly, that is a massive engineering achievement in itself.
So let's step back. What's the big picture here? What does it all mean? Why is a model that's both this smart and this efficient such a huge deal? Because this could be a real game changer. It means we might finally get top-tier AI agents running right on our phones and laptops. It means faster, cheaper, more powerful tools for developers and creators. This architecture could unlock a whole new wave of apps that have to think and react in real time, something that's been basically impossible until now.
This quote from the paper just nails it. It's about building a high-density foundation. In other words, packing more intelligence into less computing power. And that is the key to finally getting these sophisticated AIs out of the lab and into the real world, where they can actually start working for us.
And that really leaves us with one final exciting thought. For so long, we had to pick one, smart or fast. Now that that line is starting to blur, the real question becomes, what amazing things are we going to build when the most intelligent AI is also the most accessible one?
So we've all seen AI do some pretty wild stuff, right? It can master chess, write poems, even create incredible art. But what's really next? You know, the true frontier isn't just about AI thinking anymore, it's about AI doing. We're talking about teaching AI to actually understand and interact with our physical world, and let me tell you, that is a whole different ballgame. You know, this is what researchers are calling physical AI. And look, this isn't some far-off sci-fi dream anymore. It's the robot arm in a lab that's learning to pour a drink, or it's the autonomous car trying to navigate a crazy intersection. AI is literally leaving our screens and becoming a part of our physical reality. But here's the catch. For any of this to work, like really work safely and reliably, the AI has to get one thing, one absolutely crucial thing right: physics. It has to know deep down that a glass shatters if you drop it, or that a closed door has to be opened before you can go through it. It has to get the basic rules of the universe. So, okay, that raises a huge question, doesn't it? How do we even teach an AI these rules? And maybe even more important, how do we test it? How can we be sure it really gets it, or if it's just making a lucky guess? This right here is the AI judging problem. And here's where it gets really tricky. Right now, a lot of AI judges, these are the models that are supposed to grade other AIs, well, they can get pretty confused. They might look at a scene and see all the right pieces, a robot arm, a block, a wall, but they might miss the basic rule that, you can't just shove a solid block through a solid wall. They get fooled by stuff that looks plausible, even when it's physically impossible. So that's the big puzzle, right? How can we build an AI judge that isn't so easily tricked? How do we teach it to tell the difference between what's real and what just looks real? Well, a new research paper from some brilliant folks at NVIDIA and the University of Maryland might just have the answer, and it's called PhiCritic. So what is PhiCritic? Well, you can think of it as a whole new breed of AI. It's a specialized critic model built from the ground up for this one specific challenge: to be an expert judge on whether an AI's plan actually makes sense in the real world. Okay, just so we're all on the same page here, what exactly is a critic model? Basically, it's an AI teacher. When one AI comes up with an answer, the critic's job is to look at it and go, yep, that's right, or nope, that's way off, and here's why. It's that feedback loop that's so important for learning. Okay, so what's the secret sauce here? What makes PhiCritic so different? It all boils down to this really simple but super powerful idea. The core idea is just brilliant. Think about how a human expert does this. If you ask a top chef to judge 2 recipes, they don't just glance at the ingredients. No way. In their head, they're already cooking the dish, figuring out the perfect way to do it themselves. Then they look at the other options. And that is exactly how PhiCritic is trained to think. So how do they do it? It's this really clever two-stage training process. First, there's a warm-up where the AI basically goes to physics school. It learns all the core concepts. Then, and this is the magic part, it learns how to judge other AIs. But, and this is the key, it only gives its opinion after it has already solved the problem itself. It creates its own perfect answer to use as a gold standard. Okay, let's make this real. Here's a great example from the paper. The task, cook some vegetables. A robot has already put the tray in the oven, and the door is shut. The AI then has to figure out, what's the most logical thing to do next? All right, so it gets two different suggestions from two different AIs. The first one says, press the start button. Okay, seems pretty reasonable. But then, the second AI chimes in and says, push the baking tray into the oven. Now, you and I know that's wrong, but an older AI critic might actually get tripped up here. Pushing a tray into an oven is a valid cooking step, right? It's just not the right one now. And this is where PhiCritic just blows the others out of the water. Before it even looks at those two answers, it thinks for itself. It looks at the scene and reasons, okay, tray's in, door's closed, the only logical next step is to turn the oven on. So now, when it's time to play judge, the job is super easy. It just compares those two suggestions to its own perfect answer. It instantly knows pushing the tray is wrong because, hello, the door is closed. So it can say with total confidence that response 1 is better. This solve before you judge method is what makes it so stable and so accurate. All right, so this all sounds amazing in theory, but, the proof is in the pudding. The researchers really put PhiCritic to the test. So how did it actually stack up against other top models? Well, on a brand new test designed specifically for physical reasoning, PhysiCritic, it kind of crushed it. It scored a 68, which is way ahead of other big open source models like Eagle and Quen. And get this, what's really mind-blowing is that it scored a whopping 16.4 points higher than the original model it was built on. That massive jump just proves how incredibly effective this whole two-stage, think-for-yourself-first training method really is. Okay, so let's zoom out. Better AI scores are cool for researchers, but what does this actually mean for us in the real world? Why should you care about this breakthrough? Well, it means we're getting closer to having robots in our homes that can actually help out without, causing a disaster. It means safer and smarter self-driving cars that can truly understand the world around them. It also just sets a much higher standard for how we test AI. And on top of all that, it's a much more efficient way to train AI, which in this field is a huge, huge win. This really blows the doors open. By teaching an AI to understand a problem for itself before judging others, we're building systems that are more grounded, more reliable, and just smarter. And it leaves us with a really exciting question to chew on. If AI can finally, reliably judge the physical world, what are we going to build with it next? Okay, so forget everything you think you know about AI just being a tool, because a new paper from Google DeepMind, wow, it suggests we're on the brink of something huge, a massive shift. We're talking about AI not just solving problems we hand it, but actually discovering brand new knowledge, completely on its own. I mean, what we're talking about here is a genuine breakthrough. An AI just pulled off something that seriously felt like pure science fiction just a couple of years back. This is not just another small step forward. No, this is a massive leap in what AI can actually do. And look, this is not just hype. The researchers themselves say it, plain and simple. We are looking at a research paper where the entire mathematical core, the ideas, the proofs, the discovery itself, all of it came from an AI. No human intervention at all. So when something like this happens, you have to ask a pretty huge question, right? And that's exactly what we're going to dig into here. What does this actually mean for the future of science? All right, first things first. What exactly was this milestone? Let's get into how an AI actually wrote its own research paper. So the team over at Google DeepMind, they've been working on AI reasoning for a while. You might have heard they got an AI to perform at the Math Olympiad level, which is super impressive. But this is a whole different ballgame. We've gone from an AI that can solve problems humans already figured out to an AI that's generating genuinely new math. That's a huge jump. And here it is, the paper itself. Yeah, the title is a bit of a mouthful, I know, but trust me, what's inside is what's revolutionary. It's got new proofs that solve these long-standing questions in a super complex area called arithmetic geometry. And the kicker? It was all done by the AI. So who, or, well, what, is the brains behind all this? Let's meet the AI that pulled it off. It's a system called Alethea. And what's really cool is that unlike a lot of other systems that work with rigid, formal code, Alethea thinks and reasons in natural language. Kind of like how a human mathematician would talk through a problem. Its whole design is built around this really smart loop. It generates ideas, it checks them to see if they're right, and then it fixes them if it finds a mistake. And really, the genius of this design is that continuous feedback loop. It comes up with a solution, then it checks its own work, and this is the crucial part, it revises and improves if it finds a mistake. It's basically a cycle of relentless self-improvement. So yeah, it really just boils down to this simple but super powerful loop. Generate, verify, revise. And that verification step, that's what makes it so effective. See, a lot of models will just spit out an answer, but Alethea has this kind of built-in skeptic that forces it to double-check its own work. That ability to self-correct is really what unlocks its power to tackle these huge research-level problems. Okay, but Alethea isn't just this lone genius working in a vacuum. It's also turning out to be an incredible collaborator, and it's already being used to crack problems that have stumped humans for decades. And this is where the story gets really, really interesting. Alethea isn't just a tool that works alone. It can be a strategic partner. In one of these projects, it completely flipped the script on us. The AI came up with the high-level, big-picture ideas, and then the human mathematicians came in to handle the nitty-gritty technical details. I mean, that is a complete reversal of how we usually imagine humans and AI working together. And its fingerprints are already on multiple published papers, each one showing a different way it can help. You've got the full autonomy we talked about, but also cases where it was more of a strategic guide, and even one where it just improved a proof that human experts had already come up with. It's just incredibly versatile. But the team didn't stop there. They basically unleashed Alethea on something called the Erdos Conjectures database. You can think of it as a famous most wanted list of super difficult unsolved math problems. And the result? It autonomously solved 4 of them. And these aren't just any problems. These are things that have had mathematicians scratching their heads for decades. Okay, now before we all get a little too excited, the researchers are really clear about this. The AI is far from perfect, and it's super important that we understand its limitations too. The paper really emphasizes that these amazing successes are just the tip of the iceberg. For every single one of them, there are tons and tons of failed attempts. The researchers are pretty blunt about it. For now, you really need to have a good gut feeling for what the AI is bad at, just to find the kinds of problems where it might actually succeed. And one of its biggest flaws is something you've probably heard about with other large language models: hallucinations. Just look at these examples from the paper. On the left, it literally just made up a scientific paper that doesn't exist. Poof. On the right, it cited a real paper, but then it completely misrepresented what that paper said. In science, accuracy is everything. So a mistake like that is, well, it's a catastrophic failure. This chart from that Erdos problem study really drives the point home. So out of 200 possible solutions the AI came up with, just look at this. More than 2/3 of them were just fundamentally wrong. And even for the ones that were technically correct, only this tiny little sliver, just 6.5%, were actually meaningful solutions that got the question right. The success rate is still really, really low. So, okay, we have these mind-blowing successes on one hand and these pretty serious flaws on the other. How are we supposed to make sense of all this? Well, to deal with that, the researchers propose a brand new way of thinking and talking about AI's role in science. And they use this brilliant analogy that I think makes it super clear. You know how we have those levels of autonomy for self-driving cars? From level 1, which is just basic driver assist, all the way up to level 5, which is full self-driving. Well, they're proposing a similar system, but for classifying AI's contribution to science. And here's what that framework looks like when you put it into practice. It's a way to classify results based on 2 things: how autonomous the AI was and how important the math is. And look, you can see that fully autonomous paper we talked about at the beginning is sitting right here, essentially autonomous and publishable. A system like this gives us some much-needed clarity, right? It helps us actually tell the difference between a small assist from an AI and a genuine AI-driven discovery. And all of this kind of brings us to one final, really provocative thought. Maybe we're all having the wrong conversation. Maybe it's not about, will AI replace scientists? Maybe the real question is, will the scientists who learn how to use these ridiculously powerful new tools end up replacing the ones who don't?